Hey, John here. We're going to be talking about set theory again as it's used in music. And I wanted to introduce this idea of a clock diagram to convey the geometry of a given pitch class set. And I think this is a super helpful tool because it gives you a visual sort of intuition for a pitch class set and the shape and texture of that set. So I got four triangles in front of me, and I wanted to map out the four different types of triads that we think of in the West. And you'll notice in set theory down the line that there's a huge list of trichords, and I'm going to be saying triad because I specifically mean sort of the functional Western sense of that, like a major triad, a minor triad, a diminished triad, or an augmented triad. So luckily for us, a clock which has 12 hours that repeat maps very well to the chromatic scale that we use in the West. And so since there are 12 tones and 12 hours, it works very nicely. And so I'm going to be doing this for the zeros at the top. 0 and 12 are essentially the same thing. And this is because of octave equivalence, which I'll talk about in a second. But so you start at 0 here. You got halfway point is 6. And each other one is, as it should be, 1, 2, 3, 4, 5, 6, etc. So it's 0 through 11, not 1 through 12, 0 through 11. And some people will actually describe this as T and E to make sure that you're only dealing with one sort of digit at a time instead of saying like 11 and it's like, oh, is that 2 ones? And so you can sort of potentially leave out some commas, which might save some time in the long run. But so let's first map out a major triad. So what is a major triad? You might be saying, oh, it's something like C, E, G. Okay, so on a staff, let's say C, E, and G. And this is in treble clef. Cool, it's a triad if you read this. However, not everybody reads music, and a lot of people like to pass judgment on this and say, oh, you just gotta learn to read music. And sure, you should. Like, there's nothing wrong with reading music, but it's not a universal way to describe something, to put it on 5 lines that you then have to draw an extra line beneath because you don't have enough lines on your 5-line thing. So, I think that this will more immediately give you a description of the shape of a major triad, while this doesn't tell you much. Now, of course, somebody might say, well, what about this? Yep, that's also a major triad, but octave equivalence basically would link these as the same note. So even though they are differently spaced, one is actually twice the frequency of the other because it's up an octave, we're going to treat it as the same because they're both E's, E naturals. And so when we map this out onto the clock here, we're going to be talking about this in terms of like modulus, like modular arithmetic, I guess. So anything that goes above 12, you basically divide by 12 and take the remainder. So it's mod 12. So if you have a 13, that's a 1. If you have a 17, that's a 5. Okay. And so the other thing is, since we are going to be eventually talking about interval vectors, we'll sort of only look at half of this because since we can divide it in half, we can reduce the amount of information in the interval vector by half by just treating certain intervals as a reflection. So let's map a major triad here and say, okay, so 0, 4, so 1, 2, 3, 4, 5, 6, 7. So to me, a major triad is simply 0, 4, 7. Like that. And this is generic. It doesn't matter what the root note is. And so whatever it is, you just apply that interval structure to it. Now, let's say that you wanted to do a D flat major triad and you want to notate it here on the staff. So then that would mean you have to go Okay, so you have now 2 flats thrown in that weren't over here. So for somebody that doesn't already have this internalized, you're like, why did you just put in 2 extra things? Like, why is there no sort of translational symmetry? Like, why can't I just say, oh, that's the same thing, I'm going to move it over here? I mean, that's my beef with the traditional Western stuff. So here, when you map it out, you basically get, gives you a shape. You don't get any sense of shape here. You only get a sense of how spread out it is. But, this is the same distance as this, but only on the staff, because you have to know that there are naturals and flats. You can't see it there. You have to know that there are naturals, flats, sharps, all that, taken into account in sort of like these formal guidelines for, essentially punctuation. Like, you need to know the, like, put that E before I, whatever, or you have to know to put the apostrophe here, because this is, like, it's very conditional. It's very, sort of European, etc. And so this doesn't immediately give you a visceral feeling for anything about the interval content here or the pitches here. However, here, we'll just get rid of this dividing line. You can see, oh, it's a triangle. And it gives you a sense of that proportion of the triangle. Now, again, if we were to look here, so this is an E minor triad here at the end. Now, E, G, B. If we just scooch that whole thing up diatonically, that's an F major triad. And so these are actually different shapes, even though they look pretty much the same on the staff. So let's map out the same, sort of starting point, 0, but with a minor triad. So I'll do that over here. Okay, so that's the 6 right there. This would be a 3, 0, 1, 2, 3. Okay, so this is the 7 over here. So we got 0, 3, and 7. Okay, if you can read that. So we start at 0, 1, 2, 3. Okay, and 7 over there. So it looks very similar to the major triad. So this idea of happy major triads and sad minor triads, I think, is a little bit stupid and reductive, because it's essentially the same shape. Like, and to assume that you can represent a vast emotional space by sort of like frequency relations is a little bit ridiculous to me, because look at how similar they look, and I bet if you took these, if you cut them out of a little piece of paper or something, you could just flip them, maybe rotate a little bit, like depending on what any sort of situation you're in is. And in this case, they will be the same. And that's because they have the same interval vector. And so this is why I think interval vector is important, because it tells you a little bit extra about the stuff that you're dealing with. This just gives you absolutes of what each note is. It doesn't tell you anything relational or proportional or geometric about it. Here you get to see, oh, those look slightly different, but I could flip them to look pretty much the same. And, granted, you can't just flip notes in space the way that you can on this diagram, but like it gives you a sense of like that they're cousins, essentially. So if we were to find the interval vector for these, so you got 0, 4, and 7, 0, 3, 7, you might, have the intuition that's going to be the same, because look how similar those look. Like, you got the same amount of space over here, like that area is equal to that area, this area is equal to that area, that. So it's just flipped around. So basically, 0 to 4, that means you have one interval that is 4 semitones. 0 to 7, so you have one that's 7 semitones. And here, you have 3 semitones. Now, the interval vector is a 6-digit array. So, I got like basically 1, 2, 3, 4, 5, 6 spots to fill in. So we said the major third, so that's 1, 2, 3, 4. We have one of those. We have the minor third here, the 0 to 3. Except, it's 4 to 7 basically, so but that's still plus 3. So we'll put one there. Now, here's the tricky thing that I was hinting at the other video, where there's a sort of translational or rotational symmetry. You can transpose, you can reflect, etc. So the 7, since we would divide it in half here, it's actually, you want to have whatever's closest to the 0 in terms of reflection. So just as a quick example, like over here, let's say that you want a 0 to 11 interval. So it's a major 7th in Western talk. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it'd be all the way over here. So you could say, cool, I skip from here to here, but it's actually just one away if we're talking in terms of this modulus. And so it's still under 12, so it doesn't have to get any sort of remainder the way that like a 13 would. But since it's only one away, we describe that in the interval vector as a 1, because then we can reduce the amount of spaces to just a 6-digit array instead of, like having this long string of things. And that's because this little like reflective thing, it's the inversion. Okay. So in the case of this interval vector with the major triad, this 7 would be expressed as a 5. And that's because basically 1, 2, 3, 4, 5. It's 5 away because it's closer to go back up to the octave than it would be to go all the way back around. So the interval vector here is 0, 0, 1, 1, 1, 0. Okay? Now, in the case of the minor triad, let's do the same thing. So that's a 3. Got the... Okay, so a 3. Got 1. Got the 7, which is expressed as a 5. So that's 1 right there. And that... it's very messy, but it's plus 4. Okay? And those are the only intervals you have. So it's the exact same interval vector. Mic in the way. Exact same interval vector as the major triad. So this idea of happy and sad as kind of this like triad dichotomy, they're so similar, and they're just kind of an inversion of the other. And sure, I guess happy and sad are inversions of each other, but like you don't invert emotions. You invert shapes, you rotate shapes, you reflect shapes. And that's a much better way to talk about collections of pitches, I think. So just to finish out the triads here, let's look at the augmented triad. So again, we have a 0. The augmented triad is basically a major third and then an augmented 5th, which is a 0 to 8 interval. So you can talk about a 5th generically as a 5th, and most 5ths are perfect. You occasionally have a diminished 5th, you occasionally have an augmented 5th, but generally if somebody says a 5th, you're going to assume perfect. Again, this is conditional knowledge that you need to know ahead of time as like a trained musician or whatever, somebody that is aware of the culture that talks about this type of stuff. So it's going to be 0, 4, and 8. Okay. And what you will see is that there's something that you can glean from this that you can't from this. Or sorry, you can glean from this, but not from that. So if we were to map that out on the staff again, let's say in the key of E. Okay, so you have an E, a major third up from that is a G sharp. Okay, and then a major third up from that is a B sharp. But don't you want to write it as a C? Because then a C, and so then you write it as a C, but then technically because of the way that these letters work, the C becomes the root. And this is super tedious, and like, sure, they are all the same. A C augmented triad is the same as an E augmented triad is the same as an A flat augmented triad. They're all symmetrical. It's just which one you treat as the root. And that would be specified in this traditional notation by the way that you write it as a letter. So you would say B sharp if you wanted to be specific that it's an E augmented triad. So complicated as shit here. But I should finish drawing this. So B sharp, also C. Okay. So there's a lot of this like complicated stuff that you have to keep track of with this, and it's not for me. But if we were to draw it here, so you have the 0, then you need a 4, so it's going to be like here, and then an 8. Oops, I'm not doing a good job of making this symmetrical, but And if I were a better illustrator, you would see there's an equilateral triangle. And these, on the other hand, the major and the minor, they have the same collection of angles, which if you do a little number crunching, you will see that these big boys over here are 75 degrees, and then the other ones are, 45 and 60, I believe. Yeah, so basically they all have the same angles, but we're talking about angles and geometry and shape and texture and stuff like that of these pitch class sets, rather than writing specific versions of them. Like, we're talking about the abstract version, which is ultimately, I think, a lot more useful. So you see here that this is symmetrical. You can rotate it any which way. That type of information doesn't come from a system like this. And the thing is, you can do any of this sort of traditional stuff with this approach, and you just get a shape. And I think that's useful. Now, if we were to go to the diminished triad, which would be 0, 3, and 6, let's map that. So 0, 1, 2, 3, 4, 5, 6. So, okay. So yet again, another type of triangle. And of course, all these will add up to 180 degrees in terms of angles, but they take up a different portion of the octave. And so it's going to sound way different. This is going to sound bright, and it's going to sound symmetrical. And this is going to sound, honestly, incomplete, because look at, it has a whole half of the space missing. Now, the thing is, if we divide the octave into 3 equally, we get the augmented. If we divide it into 4, we get a collection of minor thirds. So if we add a 9 here, 0, 3, 9, 6, 9, you would get this additional point here. And so now it's a square. So again, you see the symmetry viscerally and intuitively and immediately, while over here, over here you don't get any of that. You don't know that seeing a little dot with a stem and like a little pound sign in front of it, you don't know that that has a symmetrical quality to it. But the shape immediately conveys this. So we got this diminished 4-part chord here. And yeah, so I think basically talking about these in terms of shape is a lot more helpful. Talking about it in terms of mood is not very helpful, because ultimately, if you have this preconceived notion of major being happy or whatever, that's your defining characteristic, rather than it's like a triangle that has a certain collection of degrees that's distinct from an equilateral triangle, then this gives you an immediate feel for it. So anyway, more on set theory later. Hopefully this is helpful. Thanks. Bye.